Hi, for today's lesson, we'll be learning about homogeneous second-order differential equations. So, a homogeneous second-order differential equation is a differential equation that has the second derivative as the highest derivative, and the equation is equal to 0. For our first example, we have d squared y over d squared, dt squared, plus 4 dy over dt plus 13y is equal to 0. Because this is second derivative, this can be written as y double prime, these tick marks are known as primes, plus 4y prime, this is the first derivative of y, plus 13y is equal to 0. So in order to solve this, we let y equal to e to the rt. R is just some number. Y prime is equal to r e to the rt. And y double prime is equal to r squared e to the rt. So now we plug these values in back to this differential equation. So r squared e to the rt plus 4r e to the rt plus 13 e to the rt is equal to 0. We find that they all have an e to the rt in it, so we can pull this out. Now we get our characteristic equation, r squared plus 4r plus 13 is equal to 0. We find that this has a very similar form to the quadratic equation, so now we use the quadratic formula. For this type of equation, the solution for x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. So now, rather than having x, we have r. So r is equal to negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 13 over 2 times 1. After evaluating this inner term, we get r is equal to negative 4 plus or minus the square root of negative 36 over 2. This negative in here indicates that it's an imaginary number. And then this simplifies down to negative 2 plus or minus 3i. So now we have our r values. This is plus or minus, so this actually gives us two values. So r is equal to negative 2 plus 3i, and our other r is equal to negative 2 minus 3i. So now our r was in here, e to the rt, so now our y1 is equal to e to this r value times t, and our y2 is equal to e to this r value times t. Now we can distribute the t, and now we get y1 is equal to e to the minus 2t, e to the 3ti, and y2 is equal to e to the minus 2t, e to the minus 3ti. Now when looking at this, we see that there are imaginary numbers and maybe hard to visualize this. So Euler's formula is used to evaluate e to raise to some imaginary number. So e raised to the I theta is equal to cosine theta plus I sine theta. In this case, our theta will actually be 3t, the number right in front of I. So e to the 3ti is equal to cosine 3t plus I sine 3t, and e to the minus 3ti is equal to cosine of minus 3t minus I sine 3t. Property of cosine is the cosine of the negative angle is equal to cosine of the positive angle. So the cosine minus 3t is equal to cosine of 3t. Now that we've gotten these values, we can get our y1 and y2. So y1 is equal to e to the minus 2t cosine 3t plus I sine 3t, and y2 is equal to e to the minus 2t times cosine 3t minus I sine 3t. Now, we find that the sine values cancel out if we add y1 and y2. So y1 plus y2 is equal to 2e to the minus 2t cosine 3t, and we let ut equal to 1/2 y1 plus 1/2 y2, which is equal to e to the minus 2t cosine 3t. The reason why we do this is because our answer may not necessarily be 2e to the minus 2t cosine 3t. So if we look at our general solution real quick, we see that we have a c1 e to the minus 2t cosine 3t plus c2 e to the minus 2t sine 3t. And the reason why we don't have any number in front of it is because the initial conditions determine this. And now if we subtract y1 and y2, we get 2i e to the minus 2t sine 3t. We let vt is equal to 1 over 2i y1 minus 1 over 2i y2 is equal to e to the minus 2t sine 3t. And yt is equal to the combination of the y1 and y2. So yt is equal to c1 u of t plus c2 v of t. So our general solution is y of t is equal to c1 e to the minus 2t cosine 3t plus c2 e to the minus 2t sine 3t. Now, if you're doing this type of differential equation and you find that, they have the both same real part, different imaginary part, you could right away just say, hey, this is c1 e to the minus 2t cosine 3t plus c2 e to the minus 2t sine 3t without having to do all this work. And some instructors may ask for end behavior. All this is evaluating y of t as t approaches infinity. So as t approaches infinity, y of t approaches 0. Something very interesting is these e raised to negative powers actually pull these cosines and sines down. So at infinity, these oscillations or cosine sine waves will eventually approach 0. For our second example, we have d squared y over dt squared minus 8 dy over dt plus 16y is equal to 0. This can be rewritten as y double prime minus 8y prime plus 16y is equal to 0. Very similar to our previous example, we're going to let y equal to e to the rt, y prime equal to r e to the rt, and y double prime is equal to r squared e to the rt. So now we can plug these values back into our differential equation. Now we get r squared e to the rt minus 8r e to the rt plus 16 e to the rt is equal to 0. They all share an e to the rt, so this can be pulled out, and we get our characteristic equation. R squared minus 8r plus 16 is equal to 0. However, we do get something very interesting. So we get r minus 4 squared is equal to 0, so r is equal to 4. So we only found one y value from the characteristic equation. So our y1 is equal to e to the 4t. We still need the second solution now. So many differential equations that have one solution often have their second solution as t of the first solution. So it is very likely that our y2 will be te to the 4t. However, we need to evaluate this. So let y equal to te to the 4t. So we need to check that this works. Y prime is equal to e to the 4t plus 4te to the 4t. This was found using the chain rule. And y double prime is equal to 8e to the 4t plus 16te to the 4t. This was also found using the chain rule. So now we plug these values back into the differential equation, and we get 8e to the 4t plus 16te to the 4t minus 8 times e to the 4t plus 4te to the 4t plus 16te to the 4t equals 0. After evaluating, we find that 0 is equal to 0. This means that it works, and this is our y2. So our general solution is y of t is equal to c1 e to the 4t plus c2 te to the 4t. And our end behavior is as t approaches infinity, y of t approaches infinity. These are both positive e values, so e raised to the 4t, that's positive, and this t is positive, e to the 4t, that's positive, so it all goes towards infinity. So I hope this helped you in understanding different types of second order differential equations, and thank you very much for watching.